All right, so today we will have Mathew Bullimore tell us about moduli stacks in 3D and X24. Take it away.
Okay, hi everybody. I hope you can see the board well and hear me well, and it's okay.
Looks good.
If I'm not writing big enough or it's not clear, please let me know. Okay, so I'd like to tell you about moduli stacks in supersymmetric gauge theories. So in a way, this is going to be a kind of continuation of a talk a couple of weeks ago from Lakshya. And the idea is basically to take everything that Lakshya said and try to turn it into some geometry. We'll try to rephrase everything in terms of geometry. And in particular to study generalized global symmetries and their Hooft anomalies, and try to frame all of those statements in terms of geometry. So a big theme of this conference, this talk series is the study of moduli spaces of vacua, Coulomb and Higgs branches of 3D n equals to 4 gauge theories. And you can often see symmetries in those moduli spaces. For example, if you have an ordinary zero form symmetry, it might act on the moduli space by isometries of it. And that's one way that you can see the symmetries. So it would be very nice, now that we know that there are other types of symmetries, higher form symmetries, one form, two group symmetries, and maybe even their Hooft anomalies, it would be very nice if there was some slightly enhanced geometric structure that captured all of those symmetries as well. And the claim is that that's exactly moduli stacks. And so these are going to be a slight enhancement, if you like, of ordinary moduli spaces of vacua, so Higgs branches and Coulomb branches. And so the idea is that I'm going to try to give an introduction to those ideas. I'm not going to try to be too systematic. I'm basically going to follow a bunch of examples. But let me begin with a bit more introduction and intuition. So one starting point for the way we think about moduli spaces of vacua is to start from a chiral ring. And that's something, so let me call that A0. It's like an algebra. And one way to think about that is that it's capturing the properties of local operators. You have some local operators, say O and O prime, and the chiral ring is capturing, in a sense, the OPE of these local operators. But because everything is nice and half BPS, there's nothing much to worry about. The operators can just coincide and they generate a ring structure. So from local operators, you get a nice ring. And given a ring like that, there's a nice way to produce a moduli space that I'll call M0, which is to take spec of that ring. And so, well, what is that? Well, it's basically invent a space such that the algebra of local operators are functions on that space. That's a standard idea. We think about local operators as functions. In this case, it will be algebraic functions on some moduli space. And in that way, we produce a moduli space, which is something like an affine variety, or even a scheme, perhaps. But anyway, it's in this kind of world of ideas, and that's one way to think about moduli spaces in supersymmetric theories. And it's a very operational way in the following sense, like you didn't need to write down a Lagrangian to say what's happening here. If someone just hands you all of the local operators in your theory and how they collide, then there's some well-defined mathematical procedure that you can do to produce a moduli space from that data. Okay, so what do I want to do today? Well, I want to kind of enhance this to discuss not just local operators, but local operators that sit at the end of line defects. So there's going to be a kind of line defect ring, or line defect chiral ring, that I'll call curly A. And what is that capturing? Well, it's not just capturing local operators now, O, but it's capturing local operators that can sit at the end of line defects. So these might be Wilson lines, for example. In fact, there will be Wilson lines throughout the whole of my talk. And in particular, it captures the kind of pictures like this, where you take two of these things, and again, you try to bring them together. So now you can collide the whole lines together, you can collide the operators together, and you'll produce another setup like this. And this will generate, again, a type of ring structure, slightly different to before. But in particular, it includes everything above, because I can just take the trivial line, and then I'll reproduce what I had above. Okay. And so the question is then, well, what geometric structure does that reproduce? Well, this reproduces what's called the moduli stack. Or rather, this will be our definition of the moduli stack. And there's a certain mathematical operation you can do, which is called proj, or in this case, it will be a stack theoretic proj. It doesn't really matter what it is for now, but it's some operation that takes this data of line operators, what local operators they can end on and how they collide, and it outputs a space of some type, some algebraic space. And the type of space that it reproduces, at least under some assumptions, which will be valid today, is a kind of Deligne-Mumford stack. Okay.
So can I here think again of A as the functions on M, or is it different than that?
No, that's a great question, because the real big difference is if you look at honest functions here, they'll be the same as honest functions here. You can't really detect the difference by just looking at functions.
Okay.
So you should think about the line defects here rather as line bundles or sheaves on the stack.
Okay.
And so that's the big difference between the moduli space and the moduli stack. If you just look at functions, you won't see the difference. You have to look at line defects or line bundles on or sheaves on it. Okay. So that's a theme of stacks and other things. Okay. All right. So let me try to put a bit more flesh on this and give some pictures or some intuition to see what's going on. So one thing we can say is that if we have this type of picture, is that this algebra A is an A0 module. What does that mean? It just means that if I have some local operators at the end of a line defect like this, I can always have genuine local operators collide with it to get another one. So in other words, A0 can act on A in this way to get a module structure. And so what does that correspond to in geometry? Well, in geometry, it tells you that you have a kind of projection map that I'll call pi from the moduli stack down to the moduli space. And so in a way, what we're going to be doing when we pass to the moduli stack is studying the fibers of this map. We're going to be studying the extra information that's captured by the fibers of this map. That's the whole name of the game. And in a way, we'd like to think about this as a kind of generalized notion of resolution of a space.
Just a quick question.
Yes.
So if L is equal to L prime in the, so is there also a module structure in that case, or is it only when the first L has to be like a trivial thing?
It has to be trivial because you see, the thing is, if I take L and I collide it with another L, then I might get some other defect, like 2L or something like that.
Yeah. Okay. Thanks.
Okay. So, all right. So there are lots of interesting kind of phenomena attached to this type of space. So I just want to give a bit of intuition. So one way to give a bit of intuition is that you can think about this map here as something like a projection, a resolution. So it's often the case that if you take your moduli space, so here it is, it looks something like a cone. Let me draw it like this. So it's often the case that your moduli space M0 looks something like a cone. In fact, if you have a superconformal theory, this is guaranteed to be true. Corresponds to an extra positive or non-negative grading here, coming from the superconformal R charge, and it gives a conical structure. And in many cases, what this map is doing is resolving the singularity in a completely standard way. So it's not really a stack at all in some cases. In some cases, it just resolves the space. And this is what we're going to call in many cases a zero form resolution. And here zero form refers to a symmetry. So for example, if I'm on the Higgs branch, we know that an Fi parameter resolves the space or can resolve the space. But an Fi parameter is attached to a symmetry, namely the topological symmetry, which is a zero form. But there might be other situations, which we'll come across, where it doesn't resolve the space in a traditional way, but it makes it smooth in a different sense. It makes it smooth by passing to a stack. And so the kind of thing we'll see is where you still have this conical point here, but above that point, I'll explain later what this means, but whatever the heck it means that there might be a discrete gauge theory, for example, a Zn gauge theory that lives at the conical point there. And the idea is that makes the space smooth as a stack. And it turns out that this is attached to a one-form symmetry. So we call it a one-form resolution. And so,
and it's a quick question. So here the idea is that when you go from A0 to A, is you add a specific set of lines, like a different type of line.
I haven't set that very carefully, but yeah, you need to basically you need to pick a specific set of lines here. Really, you're going to pick a line actually, and then look at all powers of the line. And maybe there are some conditions on which line you choose. And depending on which line you choose, you might get a slightly different resolution. So and
could you add all of the lines? Or like,
sorry?
Like, could you add all of the lines, or like well, maybe you will get to this.
I don't think I am, but yeah, I mean, you make different choices, and as you explore all the possible choices, you will explore all the possible resolutions that are available to you in that theory. So. Okay. So these are kind of two different types of resolution. There's the familiar one, which is a zero form, where you really resolve the conical singularity as a smooth variety, projective over affine. Or you can have a kind of one-form resolution where you do something different. You make the space smooth as a stack, and that requires adding a little gauge theory, discrete gauge theory at the origin. And that's we call that a one-form resolution. So you can see already that it's starting to capture higher form symmetries in an interesting way. And I should say these can combine as well. You can have what's called a two-group resolution, where you get both of these happening together. And so let me give another example. So let me call this spontaneous symmetry breaking. So one thing that this type of projection can look like is the following. So you can have a kind of projection to a singular space where you resolve the singularity fully in an ordinary sense, but you also have a discrete gauge theory sitting above every point. And symmetries can act on these spaces. So so in particular, we're familiar with the idea that ordinary zero-form symmetries can act by isometries of the kind of base space or the underlying moduli space. But the idea is that one-form symmetries are going to act on the fibers. So by passing to this extra kind of space, this stacky structure, you can see not only the action of symmetries on the underlying moduli space, zero-form symmetries, but also the action of one-form symmetries. They act on this stack. And even two-group symmetries will act on this stack. And the basic way it works is the zero-form acts on the base, or the underlying coarse moduli space, and the one-form symmetry will act on the fibers. And in some way, this is capturing spontaneous symmetry breaking of not just zero-form symmetries. For example, if I sit at a point on the moduli space, I'll spontaneously break the symmetry to the stabilizer of that point. But it also captures the spontaneous symmetry breaking of one-form symmetries at a point on the moduli space, which lead to discrete gauge fields, which is what's capturing this fiber here. This is just to give some idea that these are capturing aspects of higher form symmetries that you just don't see by studying the regular moduli spaces. So just to give a summary, the idea is to give a geometric picture for zero form, one form, two group symmetries, and their 't Hooft anomalies. Okay. All right, so that's the end of my introduction. The plan is I'm going to just look at a whole bunch of examples, starting with very basic ones. And hopefully by the end, I'll have shown you kind of all of the different types of phenomena that can occur when you do this. Okay, are there any questions about this? Okay, so let me start with an example. My first example is completely trivial. It's a hypermultiplet, something we know very well. It has two scalar fields, x and y. If you want to think of it as a quiver, it's just a box with one in the middle. So what's going on here? Well, this is really just to set up a bit of notation and to put this in more concrete form. What's the algebra of local operators? Well, it's just polynomials in x and y. The only local operators that I have, all right, let me step back a second. I should say, all of my examples, I'm going to study Higgs branches, okay? In all of the examples, exactly the same can be done for the Coulomb branches. But I'm also going to look at mirrored pairs of theories today. So you should see everything, if not in the way. But everything I will do will be on the Higgs branch. Okay, so local operators are just polynomials in X and Y. So what's the moduli space? Well, it's what we expect. It's just a copy of C2. It's just a space parameterized by the two chiral multiplets. And if we look what operators we have, we should talk about symmetries. So there's certainly a unit operator. We have X and Y. We also have X squared, XY, Y squared, and so on. And it's quite clear that these transform in SU2 reps. And indeed, that's the zero form symmetry that the system has. And that SU2 acts via isometries of C2. Actually preserving, well, to specify SU2, you need to specify that it's a Kähler isometry of C2 that preserves a certain symplectic form. But okay. So there's really not much else to say in this example. This is just local operators. What type of line defects are there? Well, there are certainly line defects in this theory, but they're not of the Higgs branch type. They're not of the type on which on which Higgs branch operators can end. So another way to say that is that there are no Wilson lines in this theory, because there's no gauge group. And so there's nothing much to do with line operators, and we just stop there. Which you might expect. There's nothing funny going on with this moduli space. It's just C2. It's not much one can really do. All right, so how do we make it more interesting? Well, let's couple to a discrete gauge field. So I want to look at a hyper, and then we're going to add a Z2 gauge theory. So what does this mean? Well, if you write it as a quiver, you might draw it something like that. One way to say more concretely is that, well, Z2 sits inside of SU2. And what does it do? It takes the two coordinates X and Y and transforms them to minus X minus Y, like that. Okay, so let's go through the exercise again. So what's the local operators do we have? Well, it's very easy, because local operators in this theory you just get by taking invariants under the action of Z2. So you just look at the things that are invariant under this action. Okay, and it's very easy to see what they are. You have polynomials in 3 variables, u, v, and w, modulo the relation uv minus w squared, where u is x squared, v is y squared, and w is xy. These are the 3 things that are invariant under this action. And they satisfy one relation. So what does this tell us? It tells us that the underlying moduli space is M0 is just C2 mod Z2. Again, that's what you expect. We're starting out with a hyper. We're gauging a Z2. And geometrically, we just take a quotient by the action. So we think of this as some conical space, and it carries an action of SO3. Why is it SO3 now? Well, Well, we've gauged the Z2 inside of SU2. SO3 is what's left. Or if you like, all of these combinations only transform in reps of SO3. So we've reduced the flavor symmetry a little bit. But now we have something interesting going on. As soon as my pages are in the wrong order. Now we have some actual line defects that we can add. Why? Because we can add a Wilson line for the gauge symmetry that we've gauged. So now we've got a Z2 Wilson line. Let me call it W. And that satisfies the relation W squared is 1, meaning if you collide the Wilson line with itself, it will become the trivial line. So what's the picture? Well, if I take the identity line, that can of course end on the identity operator. In fact, it can end on anything that we had before. That's just the local operators. But what about if I put the Wilson line? Well, that's just keeping track of all the operators that I projected out before when I took the quotient. It's telling me about those that have odd charge under the Z2 action. So the things that sit here will be A0 multiplied by X or Y. So you see the Wilson line, it kind of keeps track of everything that I lost before, right? That's what a Wilson line does. It ends on things that have a gauge charge, okay? So what happens? Well, the first thing to say is if you notice that the Wilson line W, it can't end if I set X and Y to 0. Particularly if I set X and Y to 0, all of these operators here vanish because they're all proportional to X or Y. What that means is that there's an unbroken Z2 gauge symmetry at the tip. Here. So what's the picture? Well, here's the picture. Here's our projection pi from M to M0. And we said that M0 was just C2 mod Z2 as an algebraic variety. Well, what's the stack? Well, the stack is something called the stacky quotient. Doesn't really matter what that is for today. What matters is that it keeps track of the fact that there's an unbroken Z2 gauge theory at the origin. Okay. And again here, the SO3 symmetry that we have acts on this in a standard way. So again, the idea here is that, of course, we know C2 mod Z2 has resolutions in the standard sense, but this is not one of them. This is something different. We're giving a resolution as a stack, and the way we're getting something smooth is by adding a Z2 gauge theory at the origin here. So let me make a bit of contact now with what Lakshya talked about last time and explain a bit why I want to call this a one-form resolution. Well, what's going on? Well, this theory, it has a Z2 one-form symmetry. That's just the Z2 one-form symmetry that's generated by this Wilson line. This is just a Wilson line for a topological Z2 gauge theory. So it's topological, and it generates a Z2 symmetry. And it turns out that not only does it do that, but W itself sources a background field, a background gauge field for it. So in particular, if here's my line W, and here's a small disk D2 that's intersecting it, then it has the property that it forces the gauge field, the background gauge field B2 to have a type of singularity on the Wilson line. It forces there to be some flux through the disk for the background for the one-form symmetry. And so for this reason, we call this a one-form resolution. Okay, some more slight pieces of geometry, which maybe give a bit more intuition about this space, which is, as Julius asked right at the beginning, the way you see the difference between these spaces is by studying line bundles on them. So line bundles on this is an affine space, so there aren't really any line bundles. But the point is that the stack has a non-trivial line bundle on it, and that line bundle is nothing but W. So we should think about W as a line bundle. On the moduli stack. And the way this works is that sections of that line bundle, and this is completely general, give you exactly what the things that the line defect can end on, the local operators on which it can end. These things that sit here. Okay. The basic way that this project construction works is it says, find a space such that you can think about W, this Wilson line, as a line bundle on it, and such that sections of that line bundle are precisely the local operators that you started with. Something to notice is that these are now in SU2 reps, which are not SO3 reps. For example, we could have a doublet, just X and Y, or definitely be an SU2 rep that's not an SU3 rep. And what that means is that you have an Hooft anomaly of exactly the type that Lakshya talked about last time. Okay. So you get an Hooft anomaly. What does it look like? Well, it's represented by the following SPT phase. So it's a mixed anomaly between the one-form symmetry, the Z2 one-form symmetry, and the SO3 zero-form symmetry. So here W2, well, it's the second Stiefel-Whitney class. Of the background for the SO3 symmetry. So it's the thing that obstructs lifting it to SU2. Okay. So this is the way this works. Whenever you have a line that sources a background for the one-form symmetry, and simultaneously ends on local operators that transform not in the zero form, but an extension of the zero form, you'll get a mixed anomaly of this type. One way to frame it geometrically is to say that this line bundle W, it can always be made SU2 equivariant, but it can't, there's an obstruction to making it SO3 equivariant. And that's the statement of the 't Hooft anomaly. So the 't Hooft anomaly has a very clean or clear geometric statement. It's about, they're to do with whether line bundles can be made equivariant or not on this stack. Okay. So that was my first example of a stack. So maybe I'll pause here and see if there are any questions. Okay. All right. So here is an example where the one-form symmetry, its role was in resolving the singularity in a space. Let me now give you an example where a one-form symmetry acts on a moduli stack. And the example is basically the mirror of this theory. So what's the mirror of this theory? Well, the mirror is you take a U1 gauge theory and you add a hypermultiplet, but now you choose its charge Q to be 2 rather than 1. So it's U1 with a hypermultiplet of charge 2. Another way to write that might be as a spin 2 gauge theory with 1 hyper in the fundamental. So let me not worry too much, but we can ask what the local operators are. The Higgs branch local operators, well, there are not many of them. The Higgs branch is a point. The moduli space is a point. In particular, what I do now is I take polynomials in X and Y. Now I have a U1 gauge theory, so I need to pass to U1 invariance, and I need to also quotient out by the complex moment map. And there aren't many operators left when you do this. You just get the identity operator. So it's just C. And correspondingly, the moduli space is just a point. The Higgs branch is a point. But the Higgs branch stack is most definitely not a point and has something non-trivial going on. So this is a nice example where the moduli space is completely trivial, but the moduli stack is going to have something interesting happening. And the way we detect that is again by studying Wilson lines. So let's have a look. This is a gauge theory now. It's a U1 gauge theory. So we have some Wilson lines in it, certainly. Let's call them Wn. And let's look at the Wilson lines where the charge is not negative. So here N is the charge of the Wilson line. So what happens now? Well, we get a new phenomena now. We get a phenomena where there are some line defects that just can't end at all. So if I take the unit operator, well, that can certainly end. On the unit line or the trivial line can certainly end on the unit operator. But W1, it just can't end now. For W1 to end, there has to be some operators that have charge 1. But there are no operators that have charge 1. They all have charge that are multiples of 2. Because we've given the charge 2 to X and Y now. But then W2 can certainly end. It could end on X. W3, well, that can't end. W4 can end on X squared, and so on and so forth. And so you build up an algebra in this way. In particular, to connect to the notation before, we're going to have an algebra of line defects, which is a sum of contributions from each of the Wilson lines. So here the picture is that if I have a Wilson line of charge n, the stuff that it can end on give you the component an. And we know what each of these is. It's empty if n is odd, and it's basically C. There's a single operator if n is even. Okay, so what does, if I take proj of this construction, what do I get? Well, this is fairly easy example. In this case, if you compute the moduli stack, what you get is basically what's called a point mod Z2, sometimes called BZ2. So this sounds very fancy, but all it's really saying is that if you sit at the Higgs branch is basically a point, but at that point in the infrared, there's a non-trivial Z2 gauge theory. There's a Z2 unbroken. And that's what this is capturing. It's captured by the fact here that the odd Wilson lines just can't end. That indicates that there's an unbroken gauge symmetry. So if I think about my projection map, it's kind of trivial. On the one hand, it just looks like this. The moduli space is a point, and the moduli stack, the resolution is a point with a gauge theory over the top of it. So it's worth seeing the symmetries from this point of view as well. So, okay. So this theory has now a Z2 electric one-form symmetry. Because all the matter has charge that's a multiple of 2. And that now acts on the moduli space. Okay. Acts on the moduli stack. And the way that works is that there's always, I'm not really explaining it, but there's always a natural action of BZ2 on itself. And so the one form symmetry kind of acts here on the fibers of this map. We can again ask about a Hooft anomalies and symmetries. So in this case, the Wilson line, its source as a background for the topological symmetry. So in this case, it looks something like the following. Here's the Wilson line Wn. Here's a small disk D2, then integral over D2 of the first Chern class of the background for the topological symmetry is given by the integer n. So it induces or sources a background for the U1 topological symmetry. And the fact that these objects do that and are simultaneously charged under the Z2 electric one-form symmetry is a signal of the Hooft anomaly. And the 't Hooft anomaly takes exactly the same form as it did before, because indeed this is the mirror theory to the previous example. Okay. All right. So there were two examples which kind of displayed two different types of phenomena. On the one hand, you had a kind of stacky resolution where the one-form symmetry was playing the role of a resolution. And on the other hand, its mirror, the roles are reversed. There, the one-form symmetry acts on the stacky moduli space. So it would be very interesting if we could have examples where both of those two things happen together or simultaneously. So in the last 10 or 12 minutes, maybe I'll give just some hints about an example or a couple of examples and what they look like without giving any detailed calculations. But yeah, if you have any questions about this, now is a good time. So let me give an example. And the theory that I want to look at is basically the same as before, but now I want to add two hypers of charge 2. Okay, so it's like the previous example, but doubled to double the number of hypermultiplets. So let me try to tell you what the moduli space looks like. So if you look at M0, the underlying Higgs branch moduli space, well, what do you get? You basically just get C2 mod Z2. Okay, so it's just like before. What about the moduli space? Well, the moduli space, the moduli stack takes the form of what's called a Z2 gerb over T star of P1. So instead of doing the calculation, let me just draw a picture. So here's M0. That's my conical space, C2 mod Z2. And what happens with the stack? Well, two things simultaneously happen. I'll draw this a bit bigger, just to give me a bit more room. Two things happen. One is that I resolve the space, I resolve the singularity in an ordinary sense. That's the thing that replaces C2 mod Z2 by its resolution, T star of P1. But then above every point on T star of P1, I have a BZ2. What does it mean? It just means that the Higgs branch of this theory is T star of P1 as an algebraic variety, but if I sit at any point on the Higgs branch and flow to the infrared, I still have an unbroken Z2 gauge symmetry because all the matter has charge 2. So in particular, this is what we call a zero form resolution. This is just an ordinary resolution. It's associated to the topological symmetry of that theory. It has an ordinary SO3 that acts, and it has a Z2 one-form symmetry that also acts. And these two combine into a non-trivial 2 group. Involving the zero-form symmetry SO3, the one-form symmetry Z2, and a Posnikov class theta. And one interesting thing is that you can see almost everything you want to know about the symmetries you can understand geometrically. So just to give in words some examples, so this Postnikov class describes some kind of mixing between the one form and the SO3 zero form symmetry. And one way to see it is that it's like an obstruction to this gerb being SO3 equivariant. It's similar to before. It can always be made SU2 equivariant, but there's an obstruction to the gerb being made SO3 equivariant. Because it's a gerb, that goes in 1 degree cohomology class higher and is related to the Postnikov class. Moreover, this 2 group here has a mixed Hooft anomaly with the topological symmetry. And again, that can be understood in terms of whether line bundles on this space can be made SO3 equivariant or not with respect to this SO3 action. So almost everything you want to see about the symmetries, what they are, what their higher group structure is, what the Hooft anomalies are, you can extract from the geometry of these spaces. All right. Then let me just give example 5, which is the mirror to this picture. So what's the mirror? Well, if the charge had been 1, this theory would be self-mirror. But if I change the charge to 2, what happens is that you get the usual quiver here, but then you take a quotient by Z2. In particular, what you're doing is you're gauging as further Z2 subgroup inside of the SO3 flavor that acts on this node. So let me just tell you what happens. So in this case, if you compute the Higgs branch moduli space, the underlying moduli space, what you find is C2 mod Z4 in this case. Again, you start with the Higgs branch here. Sorry, let me rephrase that. It's not clear. Yeah. Oh, it's C2 mod Z4. One way to see that is just by looking at the local operators that you had in this theory, and then only picking those that are invariant under the Z2. So this is again a conical space, and the only thing that's left is a U1. Here you're gauging a Z2 inside of SO3, and it just kills it down to U1. But then what about the resolution? What about the stack? Well, that looks like the following. You take T star of P1 and you take a Z2 quotient of it. So let me try to draw a picture just to illustrate what's going on. So if I think about T star of P1 in the following way, I draw a kind of cross section of it. It looks something like this. There's the P1 in the middle. These are the fibers at the north and the south pole. And the way the Z2 acts is it acts by rotation about this axis here, but a Z2 rotation. So when you take the quotient like this, what do you find? Well, the picture looks kind of the same. It looks like this. But now there are some fixed points of that action, yes? The 2 points here at the north and the south pole, the Z2 acts trivially there. And so what that means is if you sit at those points, there's going to be an unbroken Z2 gauge theory. So there are some non-trivial fibers at that point. And then the residual group acting is U1. So just to give some intuition, when you blow up to get a P1, this is what you call an ordinary zero form resolution. The fact that there are some BZ2s here in the is what we would call a one form resolution. And actually in this case, we know that there's a two group because it's mirror to this theory. And this is, if you combine these two, this gives you an example of what you might call the two group resolution. And you can see that the symmetries that are left over are the same as they were before, but they play an alternative role. So here the two group acts on the space. In the mirror, the two group is associated to resolving the space. And for the topological symmetry here, it resolves the space on this side and it acts on the space on this side. Okay. And well, I think this basically covers all of the phenomena that could happen in principle with some embellishments. And so maybe I'll stop there and see if there are any questions.
All right, let's thank Matt. Questions? I have a few actually.
Yeah.
So the first thing is that in this picture here, you've always turned on a phi locus parameter, basically. I mean, in some way I could. So there is now no Coulomb branch.
Yeah, I'm doing that algebraically by, I mean, I'm really doing a GIT quotient. So my choice of Wilson line is like the choice of GIT stability parameter. So I'm doing that algebraic. I'm doing the algebraic version of a Kähler quotient.
Yeah, sure, okay. But it's still you're lifting the Coulomb branch.
Yeah.
Okay. So basically, okay. So when we have we have a full moduli space with the Higgs branch and a Coulomb branch, and then you say look only at the Higgs branch, and then you can do this resolution, just like if Okay, I see.
I mean, of course, if you look at the full moduli space, it's going to have a much more intricate structure because, you know, if you sit at the origin, the whole gauge group is unbroken. So you're going to have an algebraic stack. If you want to view the whole moduli space as a stack, it's
exactly that was my question. Yeah,
it's not going to be Deligne-Mumford. It's going to be a much, you know, an algebraic stack. Yeah.
So if we have masses and if I-problems, we can't turn them both on at the same time, but we have to basically pick. Like let's say in the example,
well, you could
two hypers. Well, if we don't want to break supersymmetry.
Sorry, you want to turn if you turn masses and Fi?
I don't. Yeah, at the same time.
You could turn them on, but you might be left. You know, typically you'll be left with just points, right? You might have a number of isolated vacua. And moreover, those vacua might have discrete unbroken gauge symmetry in them. So for example, in this example here, right, I turned on an Fi, but I didn't turn on a mass.
Yeah, exactly. Yeah.
If I turned on a mass, I'd kill the whole moduli space except these 2 points. Yes.
Okay. It
has 2 vacua, but actually the Witten index is not 2. In each of those vacua, there's an unbroken Z2 gauge symmetry. Okay, and so the same would hopefully be true over here. So here I turned on an Fi. If I want to turn on a mass, I need to look at the fixed points of this action. And they'll end up being kind of 2 fixed points on the base here, right? But then again, above each of those points, there'll be a BZ2.
So would that be then the Stucky picture for the full moduli space, just these 2 points? Or, I mean, have you thought about it? What would be the full modular space?
No, not except that it you know, it has to be in a realm of algebraic stacks in some sense.
Okay.
To say that, yeah. Here I'm turning at least one. More is okay, but less perhaps not. Yeah.
And do you have things to say about symplectic duality, which is now like a stacky version of symplectic duality?
Yeah, I don't have anything to say except that it should exist.
Okay.
And should extend
Okay.
and should extend what's already been done. Yeah.
Okay, very nice.
But I mean, maybe one thing to say is that one needs to understand how to build the Coulomb branch stack first of all.
Okay.
Which I didn't talk about. Abstractly, the definition is exactly the same. But the point is, like, it's very difficult for someone just to hand you all of the line defects and what they end on, right? But I think, for example, the BFN machine can be bumped up just a little bit to capture the second structure.
Okay. Do we have any more questions? No. So let's thank Mathew again. And we'll go off the record.
Yeah.